Hello and welcome to this video. In this video we're going to be looking at the idea of stationary waves. So everything that we've done up to this point, all of the waves that we've looked at have been what we call progressive waves. Okay, so what a progressive wave is essentially a traveling wave. So it's a wave that, let's say, propagates, to use the correct terminology, in a specific direction. Okay, meaning that it moves in a certain direction. So we've already said that this sine wave is going to move along. So the whole wave will continue to move this way. This is what we call a progressive wave. Now, stationary waves are therefore the opposite of progressive waves. And it might be a surprising thought to think, how can we have a wave that's not moving and just staying stationary? Surely all of the waves, like light and sound and all of those kind of things, should all be progressive waves. And you would be right. Okay. However, when we have these progressive waves, we can have two progressive waves that interfere with each other, and that's what's going to happen here. So the way stationary waves form, we're going to talk about stationary waves forming on a string to begin with, but this is also true for other cases, which I'll show some examples of as well. So let's say we have a string. Let's make it a guitar string. That tends to be the common example. We have some guitar string of some length L. Okay, so some length L. And what we're going to do is pluck the string, and what that does is it causes a wave to travel. So I'm going to draw this wave in red again. So it causes a wave to travel along the string. Okay, this wave, this red wave, is a progressive wave. Okay, because it is moving along the string, it will move up. But what happens at the end of this string is, at the top of the guitar, you have a piece of like plastic called a nut, and it basically causes that wave to be reflected. And so what happens then, we get a reflected wave, and when this wave is reflected, it comes backwards like this. So I'm going to draw it like a dash line. Now obviously the blue wave is also a progressive wave because it's going to get reflected and move backwards, and so it's not going to form this instantaneously and then destructively interfere all of it, and then we have no wave. That's not how stationary waves work. What's going to happen is, as this red wave travels along in this direction and the blue wave travels along in this direction, they superpose. Okay, so we have two progressive waves. And it's important to mention at this point that they have to meet some conditions. So in this case, they have to have the same frequency. So two progressive waves with the same frequency. We'll put that in the commas here. So two progressive waves with the same frequency, traveling in opposite directions. Traveling in opposite directions. Superpose. Okay, so this is the important thing here. They superpose, and they will, therefore, if they're superposing, will constructively interfere in some places and destructively interfere in other places. Now, it's very difficult to draw moving waves, so I have a little bit of a animation that will hopefully help. So in the same way that I've drawn it here, we have a red and a blue wave that are traveling in opposite directions. And so what you can see is that if we take these points here, these red dots, this is where we always get destructive interference. Okay, because we're always, if you looked at the amplitude of the red and blue wave as they travel through here, they're always opposites along all of these, so we always get destructive interference. these positions are called nodes. Okay, now I'll draw a little bit of a diagram to show and label what everything is, but you can see that in between these nodes we actually get constructive interference all the time because they're always in phase at this point. They're always in antiphase at this point. And therefore we have a mixture of the progressive waves being both in phase and in antiphase at the same time. Now the blue wave in this case is moving in this direction and the red wave is the reflection. And so we're getting this stationary wave because this whole string has a finite length. Okay, so it's not moving. We just have the string itself is vibrating up and down, and then some positions are stationary. And so this is a stationary wave. Okay, now to finish up this idea, we're going to introduce some terminology. I'm going to explain what this means in a second. So two progressive waves with the same frequency traveling in opposite directions superpose. They constructively, so I'll put a full stop here, they constructively interfere to form antinodes and destructively interfere to form nodes. Okay, this box here is going to be a very common exam answer. Okay, so they will usually say to describe the formation of a standing wave. This is your answer to that question. So you have two progressive waves with the same frequency traveling in opposite directions. They superpose. They constructively interfere to form the antinodes and destructively interfere to form the nodes. Okay, what I mean by nodes and antinodes, I just explained briefly, but to put it into more detail, let's say we have let's put an equilibrium line here, and then we have a wave that's sent down here. So we have a wave that's sent down here. We know the reflected wave is going to cause this kind of effect. Okay, where this string is just going to oscillate between the dashed line and the solid line. So it will continue to go back and forth, and it will be basically everything in between. So you can get an instant, for example, where the string might have this kind of wave, okay, because it's constantly oscillating between these 2 points. So this is going to help us define what we actually mean by the terms node and antinode. So these points here, which I'm going to label with the letter N, these are nodes. Okay, and a node is just a point that has a point with 0 amplitude or even 0 displacement. Okay, because these positions are never going to move from where they are. So the node is just the points that are fixed points with 0 amplitude. We can also get antinodes. So if you can kind of assume if nodes are the points where we have 0 amplitude, antinodes are the points with the maximum amplitude. Okay, so this is your general idea of what a stationary wave is. Now, there are different what we call harmonics of stationary waves. Okay, so different harmonics, because like I say, these are usually used in guitar strings. It can then apply to any stringed instrument, so like violins, violas, cellos, basses. All of these things will also have the same effect. But we could then also apply it to wind instruments. We could apply it to like trumpets, horns, saxophones, whatever it might be, you can always apply the idea of music is mostly down to this idea of stationary waves. So let's have a look at some harmonics. So what we're going to say now is we're going to assume that there is a fundamental harmonic, okay, meaning the smallest harmonic we can get. Okay, this idea of a fundamental harmonic basically is just saying it's the first harmonic. Okay, so it's the first harmonic that we can get. Okay, and the way that's going to happen is that we have a stationary point at the end, assuming this is a guitar string. It's then going to have a full half wavelength to get to this point, then get reflected, and then come back to the start. Okay, this is the first harmonic where these are the nodes, and in the middle here we have an antinode, the point of maximum displacement. Okay, this tends to be the ones that we're going to look at the most, fundamental harmonics. And there is actually an equation that we need to know that explains how we'd find the frequency of a fundamental harmonic, because these things we know, because they're sound, if we have different harmonics, they're going to have different frequencies, because we can form different pitches of sound based on essentially where you're putting your finger along the guitar string. So the way that we do this is going to be quite alien to most people, but what we are going to do is we're going to say that we start from this idea that frequency is just going to be the speed of the wave divided by the wavelength. Okay, let's assume this this wave, or this length of string, has a length L. So it has a length L. That means that the wavelength of this, since this is half of a wavelength, the wavelength has to be 2 times that length L, because this is just half of it. We'd get the other half if we went, if we had double the length of string. Okay, so this is an important point here. Okay, so we can say now, knowing that measuring the wavelength is going to be quite difficult, we can just measure the length, and then because we can see which harmonic it is, we'll instantly know what the wavelength of that thing is. Okay, so we could say now, we could rewrite this out as F is equal to C over 2L. Now, how do we work out C? C is going to be very difficult to work out, because we're trying to, usually when we work out the speed, we're going to be looking at distance over time. In this case, the distance is the wavelength and the time is the frequency, or time is 1 over the frequency. So what we're going to do is say that this speed, we're going to refer to a bit of what we call material science, and we say that the speed of a wave through a specific medium, we could write as saying it's the root of the tension in the string divided by its mass per unit length. So T is the tension in newtons, and mu is the mass per unit length. So it's almost like a density, and this is in kilograms per meter. Okay, so it's almost like a density. So a density would be mass per unit volume, but instead of having volume, we have a length. So this is what we would technically call linear density, but you don't need to know anything about that. Just know that this square root of T over mu is going to tell you the speed at which this thing, at which this harmonic is moving at. Because of this, we can then replace the C with T over mu, and then we can say that the frequency of the first harmonic, so I'm going to call it F1, is equal to 1 over 2L multiplied by T over mu. Now this formula is in your formula sheet, okay? These two aren't, okay? So I'm going to put a star next to these because these two aren't in your formula sheet, but I think these two things are good to know. So you can be tested about this idea that lambda is 2L for the first harmonic, and I think this will provide a little bit of a shortcut for some questions where they'll usually ask you to then work out the frequency and the wavelength and then use that to work out the speed. If you know this relationship, you can just do the tension divided by the mass per unit length and you'll already get the speed. Okay, so it's good to know that this equation is identical to F equals C over lambda. We've just changed how we're going to calculate the wavelength and the speed. Okay, now we can say what happens if we increase this frequency, because this frequency 2L is a constant value. The tension in the string is going to be a constant, and so is its mass per unit length or its linear density. So this frequency is a very specific frequency where if we hit that frequency or we pluck the string at that specific frequency, it will form that harmonic. If we were to increase the frequency, it's then not going to form a harmonic until we get to a second harmonic, which is another very specific frequency. So now we can look at a second harmonic. So the second harmonic, since in the first harmonic we only had half of a wavelength, the second harmonic we're going to have one full wavelength. So the second harmonic is going to look something like this. Okay, and then it will be reflected and look something like this, where we still have the same length of string. So L is still the same, so we still have a length L, but in this case the wavelength is L. Okay, and these 3 points here, we now have 3 nodes instead of 2, but we have 2 antinodes in the middle here. This is going to be a specific thing to this frequency. There is a specific relationship between the first and the second harmonic, and there's a general trend on this. If we wanted to work out the the frequency of the second harmonic, sometimes also referred to as the overtone. Okay, but this is kind of old school language. You don't really use this anymore, but in case you see this idea of an overtone, this is what we mean. So if we take the fundamental frequency and we double it, so we take the fundamental frequency times it by 2, we get the frequency of the second harmonic. Now, just to prove that this is true, notice that the only thing that's actually changed, the tension in the string could remain the same. We've got the same string, so it has the same mass per unit length, but the wavelength have changed. So F2 is just going to be 1 over L times root T over mu. So all we've done is double the F1 to get to F2, which is why this is true. Okay. Now we could do this again for the third harmonic. If we did 3 times the first harmonic, we'd get the third harmonic. If we did 4 times the first harmonic, we'd get the fourth harmonic, and so on. Okay, so generally we can take the first harmonic, multiply it by whatever harmonic we want it to be, and we'll get the frequency for that harmonic that we'd have to drive. This skill of being able to depict, if we know what the harmonic is, how do we know what the wavelength is going to be one that you will just pick up. To be able to know how to draw which harmonic it is, just know, so a general hint for that is know that the number or the amount of antinodes, I'm just going to write that as AN, will be equal to the harmonic. Okay, so if you'll notice, the first harmonic up here has 1 antinode, the second harmonic has 2 antinodes, the third harmonic is therefore going to look like this, because it then has 3 antinodes, and so on. Okay, I'm now going to split this video a little bit, and I'll talk about more to do with what happens if we have a wind instrument rather than a stringed instrument in the second video, and then we'll also look at some other applications. For example, your microwave oven at home, that works by standing waves as well. So yeah, hopefully all of this makes sense up to this point. Stay tuned for more information about all of this, and thank you for watching.